won't say anything about the people who didn't. Anyway, so I've gotten, let me go a little bit out of order. Maybe the first part is remind you what we've talked about last time. We talked about harmonic maps. Some of the central characters we were talking about harmonic maps between surfaces. We pulled back a metric. It decomposed by type, dz squared, dz bar squared. That's the 2, 0 part. That's the 1, 1 part. That's the 0, 2 part. And we found two actors in our play that were important. This Hopf differential phi, which was holomorphic, and this holomorphic energy H. This is, I won't say much more about it. It is some version of energy density. You see that it is pushing forward. Another way of saying this is I push forward the complexified tangent vector d by dz, and that push forward vector, I take the length squared of it in the target, and that's h. Okay. And they were related by this Bachner equation. Now, I got some questions, and let me go out of order. So I'm going out of order in my notes, which is dangerous, but I think this will fit. So let me go a little bit out. Let me try to answer some questions. So I got a lot of questions about what is a quadratic differential? What is a holomorphic quadratic differential? And of course, I've been talking about this Hopf differential phi, which has the local expression w rho of w, w, z, w, z bar, dz squared. Doesn't matter what it is. Well, so what is a holomorphic quadratic differential? Well, a holomorphic quadratic differential is a tensor expressed in local complex coordinates z as some function of z dz squared. And holomorphic means that the stuff out front, the phi of z, that function, is holomorphic. And that's it. Maybe you're used to holomorphic one forms. So for example, if alpha of z dz is a holomorphic one form, and these are common on Riemann surfaces, then if you square alpha, that's a holomorphic quadratic differential. Not all holomorphic quadratic differentials are squares of one forms, but squares of one forms are holomorphic quadratic differentials. So if you feel comfortable with this, then you have no excuse but to feel comfortable with that locally. And then there are various statements one can say using Riemann Roch, for example, computing the dimension of the vector space of these things and that sort of thing. I don't want to go into that classical Riemann surface theory or dimension one algebraic geometry. Let me take a different point of view and try to draw you a picture of these things. So how to imagine a phi which is written locally as phi of z dz squared? Well, this is a holomorphic object. So holomorphic objects are almost entirely determined by their divisors, by their zeros, right? If you have two holomorphic objects of the same tensor type that have the same zero set with the same degree, you divide one by the other, then you have a non-vanishing holomorphic object, And on a compact surface, non-vanishing holomorphic functions are constants. So if you know the zeros, you know the holomorphic quadratic differential up to some complex multiple. Make sense? So, so part one is that the zeros of phi determine phi up to a constant. So the first thing we do when we're thinking about the shape of this holomorphic quadratic differential is we look at where it's zero. Here, here, and here. Okay? That tells you a lot about it. But now we have these vast regions where it's not zero. What can we say there? Well, so let me draw a picture related to that. So 2 away from zeros, we can change coordinates. Now, let me take a step back for a moment. I'm answering this question about how to see a holomorphic quadratic differential. I'm going to lead you through a 10-15 minute discussion of this. And, it's all self-contained. Remember that at some point, these holomorphic quadratic differentials came into our discussion because we're talking about harmonic maps. So eventually your questions will have to be, okay, with that shape, what does the shape of that differential have to do with the shape of the harmonic map? So that's always in the back of your mind. Don't be surprised when we come back to it. Okay? So, but we can change coordinates. There's a number, and so this is my simplest way of getting at. It's the slickest way. It's maybe not the best way to get at the picture I want to do. So I'm away from the zeros. So I have this phi of z dz squared object locally, right? Right? That's its local expression. Away from the zeros, I can take a square root of it. I don't have a problem with branching because there's nothing to branch around. The square root is determined up to a plus or minus. Right? This is now a locally defined holomorphic one form. What do you do with holomorphic one forms? You integrate them. So just take your favorite base point away from this zero, p naught, and then if there's some other point, q, take a path from p naught to q, and integrate that, and you'll have a number. Okay? And I'll call that zeta of q. Okay? Why do I do this? Well, look at d zeta. Zeta was this locally defined function. Look at d zeta. The fundamental theorem of calculus tells you d zeta is plus or minus phi, square root of phi. Right? So if I square d zeta, that's the same thing as phi of z dz squared. It's the same thing as phi. So I've now found a really good coordinate to express phi in terms of. So canonically associated to phi, there is this coordinate zeta. So what does that mean? So redrawing my picture, I already, I had this surface, I had this divisor, I have this patch, and now I have this coordinate down to the zeta plane canonically associated to phi. So anything geometric in the zeta plane is canonically associated to the quadratic differential. Quadratic differential determines the coordinate, so the geometry of this coordinate domain it creates a geometry up here. So let me show you the geometric objects I care about. I care about the horizontal lines in the zeta plane. It's called the horizontal foliation. And I care about the vertical measure. So if zeta is psi plus iota, and here's the zeta axis, and there's the eta axis, I care about the following two objects. I care about where the imaginary part of zeta is constant, so this eta. I care about that foliation, so that'll be some horizontal foliation of phi, and those lines will pull back to some partial foliation up here, right? And I care about counting distances between lines with respect to a measure. So I care about the absolute measure d eta, and that will pull back up to here as well. And what do I mean about that measure? I want to be able to measure curves. So this curve gamma, if I want to measure it, and then the notation used to measure it is you look at the intersection number of this measure, and this is usually called the horizontal measure, the transverse horizontal measure of phi. I'll look at the intersection number of the horizontal measure of phi against the curve, and what do I get? This is a dumb statement, but you'll understand. 1, 2, 3 plus 1 makes 4, 5, 6, 7. I get 7. How many leaves it crosses as a measure? And I'm using absolute value, so I don't cancel. Okay? And so that gives some. So I have the same thing here. I guess it goes up one more. And so that gives some foliation on the surface. Another way of expressing that foliation is, well, maybe we won't go there. But then we can fill this thing in. So I told you that over here we have, these full leaves, but we also have this divisor. And what happens at the divisor is that the foliation has some singularities having to do with taking, square root and branching. So we had one there. That one is some singular. That's a first order 0. Has that singular expression? It looks like that. Maybe there's one like this. Back over here, we had something else, and the foliation is well defined on the surface. And it kind of wanders around in a complicated way and fills in, not really sure what's happening here, but you get the idea. We have some pattern on the surface of leaves, and the leaves do not cross each other, and they wander around the surface, and we get something very complicated. Does that make sense? And that's just the way you might picture a holomorphic quadratic differential. It has some singularities. As an invariant of the singularities is the order. The order determines a sort of if it has order k, then it has k plus 2 branches coming out of the singularity, and then there's leaves that fill in, and that is the picture of a holomorphic quadratic differential, one of the foliations. There's another foliation. Similarly, we have a vertical foliation, f vert phi, and this is going to be locally where psi equals real part of zeta is constant, and we'll have the same measure, u vert phi, which is locally d psi, and then that's going to, and when I draw that, it won't work well. Okay, I really only do have yellow. So that will be leaves coming like this, and those leaves will lift up like this. They'll come out in other directions, and if I try to draw too much, I will get in trouble, but you get the idea, right? There's these two characteristic foliations. Another way of saying it, shouldn't have done that, is that the horizontal foliation is the same, it integrates directions v with phi of z, dz squared on v positive. What do I mean? Take the v is an a d by dx and a b d by dy. dz is a dx plus I dy, and the whole thing is squared. dx on this is a, dy on this is b, so I have an a plus ib, I square it, I get a plus ib squared, I multiply by phi, I get a number, that's a complex number. I want to pick v so that complex number is real and positive. And so this, in any point, there'll be like one pair of directions v where I'm real and positive, and otherwise I'm not. Okay, that picks out the foliation. It's an analytic point of view. Great. Say it again. The blue one? Negative. Okay. So now you have a question for me, right? Your question for me is, okay, you spent the blackboard, this whole blackboard, talking about the picture associated with a quadratic differential that has to do with all quadratic differentials. What about the Hopf differential? What does the picture have to do with harmonic maps? Right, that's how we got into this game. So, and the point is that the horizontal foliation integrates the directions of maximal stretch. The vertical foliation integrates the directions of minimal stretch. What do I mean by maximal and minimal stretch? Well, if I have a map U, then what does U do to a small little ball, infinitesimal ball? It takes it to an ellipsoid, right? And there are two directions. There's one direction where it gets stretched the most, and there's some other direction where it gets stretched the least. And if I plot those directions on the surface, then I'll get these two foliations. So these foliations are telling you how they are stretch lines on the domain surface, telling you how to take the domain surface and stretch it so that after you stretched it, you reach the target surface in a harmonic way. That make sense? So that's really the shape of the harmonic map, and in some sense that's why the Hopf differential is interesting. Great. Maybe I'll say it's, no, I won't say that. So for example, let's do a couple examples of harmonic maps just with this point of view in mind, just to see what happens. Let's think of a harmonic map. Now, these aren't compact surfaces anymore, but that's okay. I assert that you already know some harmonic maps. So let's look at a harmonic map from the complex plane to H2. And what I have in mind for this harmonic map is I'll take my coordinate z on the plane, and z is, of course, in the natural coordinates x plus iy. And the first thing I'll do to z is I'll map it to R, and I'll just take the real part of z. So z, x plus iy goes to x. That's got to be harmonic, right? Right? I mean, Laplacian of x equals 0. because it's got d by dx squared in it. And then I'll take, so now I'm down here to the line, and I'll take the line up into H2 into some geodesic, gamma. And that'll be an isometry. So the composition, z equals x plus iy down to x up to here, is some map. Isometries should be preserve harmonicity, and they do, because they're just keep the metric is the same. So if this is harmonic to this metric, when this pullback metric is the same as that metric, so that composition should be harmonic, and that is. So the map of the complex plane to a geodesic is clearly harmonic. Let's draw the complex plane one more time, and you can see what's happening. I have all of the lines y equals constant. They are all getting mapped directly onto the real line r there by x plus iy goes to x, and all of the vertical directions are getting crushed. So here you really see that the minimal stretch directions, the directions which have least stretched, well, those are vertical. There's no smaller stretch other than completely collapse. Right? So those are vertical. And what's maximal is the horizontal directions, because these are just getting preserved. The whole map has the differential is entirely in the x direction of norm 1. And so so we can see this, so not only do we see this harmonic map, but we also see the pattern of the harmonic map. And in fact, if you were to, let me make a comment, if you were to compute the Hopf differential, we can compute that this Hopf differential is exactly dz squared if you pulled back this metric, but we don't even have to compute, because look, you're looking for a holomorphic object on the plane. And what do you know about that holomorphic object? It's got to be translation invariant, because harmonic map is translation invariant, translation left to right, and it has to be translation invariant up and down, because the harmonic map is. So I need a holomorphic function on the plane, which is translation invariant. That's got to be a constant. So I know this quadratic differential up to a real constant, and might as well be 1. Okay? So we see that as dz squared. Let's reverse the process. There's a chance I'm going to get myself caught. Nope, I'm not. I think I'll be okay. Another example, let me reverse the process and say, find a harmonic map from C to H2 with Hopf differential phi. Well, it's on the plane. It'll be some function times dz squared. What's the simplest function I can think of that's not 1? Z. That's the first order polynomial. Okay? Z dz squared. Well, okay, so we know that the foliation for z dz squared looks like, and I'll say the horizontal foliation, just to start. Oh shoot, how did I? It's going to look like, if I set it up like that, you can work that out. Well, you can see that if I take the direction d by dx, then dz on d by dx is 1 times x times z is z, real part, well, on a real line, this will be positive. Anyway, it's easy computation. So that's what the horizontal foliation looks like. And now Let me do something I will justify a bit later on. Let's think about this. I said this is on the plane. So I drew this foliation on the plane. Well, the plane is really big, right? So I drew it near 0. Let's draw it out where it's like 1 trillion. So here it's still going, right? It's way over there, too. That's the leaves. Now, when you're way over here, the harmonic map just sees full leaves like this. The harmonic map doesn't really see a 0. The harmonic map thinks that the quadratic differential is just d zeta squared. It thinks it's doing this. I can justify that later, but let me just accept it for a minute. It thinks it's just collapsing and going to a geodesic. So way over here, it thinks it's getting mapped to a geodesic. So, oh, I'm sorry if I'm out of camera range. So way over there, it believes this map is very close to mapping to a geodesic. Similarly, way over here, the harmonic map thinks it's mapping to a geodesic, because it's basically d zeta squared. So it thinks, so the map looks something like this. And it way down here, which I won't draw, I promise, okay, it looks like it's mapping to a geodesic, so it looks like this. So this harmonic map with this Hopf differential maps the complex plane into an ideal triangle. And that's the picture of it. If you like, we can use Mahan's observation that this Bachner equation doesn't depend on the phase. If I take the norm of z dz of z, I get r. So if you're like really excited by this lecture, and I know everyone is, so you could try to, so the equation Laplacian log h is 2h minus phi squared over h minus 2 is really, if I take Laplacian to be d squared dr squared plus 1 over r d by dr, it's really an ODE. It's saying that log h double prime is 2h minus 2, oops, I forgot the 2, r squared over h minus 2. That's some ODE, which you could solve. You can solve it out exactly. I think this is one of the Panlevet equations. Do you remember, Subhojoy? I'll say 6, and that'll be safe. Because I think it may be 3, but I'm not sure. So anyway, you could actually solve for this harmonic map if you wish to, in terms of something like a solution to Panlevet. But that's what it looks like. Okay, so that's what I wanted to, so that's something about like the shape of these harmonic maps. You should really think of these quadratic differentials as saying how much you're stretching. Okay, back to the Teichmuller theory. Uh-oh. So we had a map from the Teichmuller space of this surface M or S to these quadratic differentials on the base point, which took us from, so here's the picture again. I have sigma. I have this vector space at sigma of the quadratic differentials. And to some point rho, we associated this Hopf differential, phi of rho, which was constructed by looking at the harmonic map to rho, pulling back rho, looking at the 2, 0 parts, and that gave some quadratic differential. So there's some map from Teichmuller space to quadratic differentials. Okay? What can we say about this map? Well, the first comment to make is that this map is continuous. I'm not going to justify that much. What does continuous mean? It means that if I change rho by a tiny little bit, then the Hopf differential changes by a tiny little bit. It's not really a surprise. If I change this target by a little bit, the harmonic map should change by a tiny little bit. That's a consequence of the harmonic map being unique, more or less. Shouldn't really jump. Otherwise it would violate uniqueness. And then when the map changes a bit, so do the tensors associated to the map. So continuous should be fairly simple. The next part I was really going to do for you, which is that if we had rho 1 and rho 2 not equal, we had two different points, two different hyperbolic metrics, then the Hopf differentials are really different. Yep. Oh, that's what you mean, right? So this is actually very. I wanted to do this for you because the proof is once again the maximum principle. The point is, you already know that if I look at the HIs, each one of those H's in this pullback, I want to pretend that we have two maps with the same Hopf differential. I want to say that I get the same metric. Well, they already have the same Hopf differential, so I just got to show that they have the same H. Because then from the H's in the Hopf differential, I reconstruct the metric. But how does the H relate to the Hopf differential? Well, it relates like this. Remember, the phis are the same, there's no I. So I could look at Laplacian log, say H1 over H2. I want to show H1 is the same as H, so I want to show that's 1. And, so now subtract the other sides. Pretend it's not 1. If it's not 1, there's a place where it's biggest. Look at where it's biggest. Use the maximum principle. This equation has a maximum principle. The maximum principle, when the dust settles, tells you that H1 can't be bigger than H2, H2 can't be bigger than H1, but so they have to agree. It's really amazing. So, so the Hopf differentials distinguish points. The last point I want to make, and this I will spend some time on, is that this map phi is proper. What do I mean by that? I mean that if I take a bunch of metrics rho and I let them go to infinity in Teichmuller space, they get extreme, they start to degenerate. Well, if I look at the Hopf differential, then this will go to infinity in that vector space. In other words, it's not, so sitting here at sigma and looking at a bunch of rows heading off to infinity, when I look back in the vector space at what phis I get, it's also going to head off to infinity. It's not going to stop. I'm not going to get just some small little ball of Hopf differentials. I'm going to get the whole vector space. Does that make sense? That's the claim. Why is this true? So everyone understand the claim? So why? Well, the reason is, from time to time in doing geometric analysis and PDEs, there's a time to do PDEs, there's a time to do geometry. So, so here's our picture. Here we are on M sigma, and I have on M sigma some basis for pi 1. I don't need the efficient basis. I just need, I don't know. Anyway, pick as many as you want. I don't care. Okay? And now, if M rho is far out in Teichmuller space, one of those curves has gotten big. If they all stay small, they all have length less than 20, then I haven't degenerated. Something has to get big. So, somewhere, maybe sometimes people like to think about, so this is a bit of a cartoon. Maybe there's a short curve here, but if there's a short curve there, then there's a really long curve that came through it. Does that make sense? So if it's going to pinch, or it's going to, maybe what's happened to the curve, to whatever curve this is that it's twisted a lot. Come over here and it's twisted a lot. So that somehow some curve has gotten long, either because, as Halsey Royden once told me, you've either strangled the surface or you have wrung its neck to introduce violence late in the lecture series. So we've done one or the other to this surface, and something's gotten long. Well, if a curve has gotten long, what do I know? Then you can look at a small, so let's isolate this picture. I have a curve here, and then over here it's gotten very long for some reason. I'm not really sure why. Okay? Either twists or stretch or something. So I could look at some annulus around this curve. Right? And every curve, every parallel curve in this annulus, if this is the geodesic, is at least that long. Right? So that every parallel curve in this annulus has been stretched by at least the length of the geodesic. Does that make sense? So what do I know? I know that if I look at the energy of the map restricted to the annulus, well, that's at least, the energy of the whole map is at least however much energy there is restricted to the annulus. The energy restricted to the annulus is some integral. Well, it's at least the stretch of into theta direction. I'm getting late, so I'm skipping notation. Everyone sort of get what I mean? Okay. And so, but that's going to be at least W star d theta, d theta squared. I'm sure I've now dropped a constant. I'll put it back in there. Okay. The length, this is Schwarz inequality. Length, integral of a square is at least the integral squared, right? And this has something to do with the length in rho of this object, squared, somehow compared to the length of the object back in sigma, and that's going to infinity. Does that make sense? So each one of these curves is being stretched by this length. So I have a comparison for energy of the length here versus the length there squared. I integrate, I get something very large. So the energy has to go to infinity. Okay? It's a very different sort of argument than we've done before with the analysis, so I wanted to bring it up. On the other hand, so I know the energy blows up. Now maybe in the interest of time, I'm going to skip a step. And the point is that if I look at the size of phi, this is bigger than something like, I think, 2 of them is bigger than the energy minus a constant. This is an easy bit of algebra, which I'm going to skip. Sorry, this is algebra. I'm happy to show you the 5-minute manipulation of symbols later. And the point is, this goes to infinity, so this phi blows up. Are you very dissatisfied with that? The algebra is a little bit of messing around with the WZ and the W's. So here I have a WZ times a WZ bar. Here I have a WZ squared plus a WZ bar squared. So the geometric mean, arithmetic mean, AB less than A squared plus B squared over 2 comes into play. Okay. All right, but I'm just going to leave it like that. And so what have we learned? So I'm sorry to skip that, but otherwise I have to give a third talk. So I've learned that this map phi is continuous, 1-to-1, and proper. So I have learned that phi from Teichmuller space of M to these quadratic differentials at this base point is a homeomorphism. So reading it the other way, these quadratic differentials parameterize the Teichmuller space. Yeah. Tell me what to do with my finger. Here? Oh, d theta. I'm sorry. No, okay, I guess it's terrible. Okay? That way. Okay, so this map is a homeomorphism, and the point, again, is that Hitchin provides, with far more sophisticated arguments, a more sophisticated version of this. For, let's say, SLNC. Maybe this is Hitchin and Donaldson at this point. Okay. Where one parameterizes the representation space of surface groups in SLNC by a prim bundle over a vector space of holomorphic objects. Okay. So it's much more sophisticated, but this is really the baby case, and the more sophisticated version is why I put such effort into showing this was a homeomorphism. So we now know, here's sigma, here's this vector space, and I can look at some ray in the vector space t times phi 0. And that gives me a family back in the Teichmuller space of metrics rho t. Because it's a homeomorphism, there's for every ray here, there's a family there, and somehow it's vice versa. So what can we say about this family for t small? So this section is about, consider t small. And there's actually a fairly substantial theory here, and I was hoping to say more about it, but I'm sure I'll run out of time. But let me see what I can say in 15 minutes. So what do we know? We know that if I pick a point on M, and I look at this function ht, by which I mean the h corresponding to the teeth metric rho t. In other words, I have this path rho t. I look at harmonic maps from sigma to rho t. I look at the holomorphic energy that h associated to that. I'll call it ht. And so what I know about ht, I know ht satisfies the following. It's at least 1. That was the maximum principle. And at time 0, it's identically 1. So what does that tell you? That tells you that the time derivative of ht as a function on the surface is identically 0. As a function. That's right, because it's at least 1 when time's bigger than 1. Take a point, it starts out at 1, it gets bigger. Time derivative is identically 0. You can actually compute, let me just tell you an algebraic computation, that the Jacobian determinant, the Jacobian of the map, Wt, say, from M sigma to M rho t, is, I'll say Jt, it's this h minus v squared over h. Oh, and I said t, so let me put a 0 here and pull out the t squared. Okay? This is the analog of something maybe you know from complex analysis, that the Jacobian of a map is wz squared minus wz bar squared. And I've just made that Ramanujan. If you've ever worked out in a planar domain what the Jacobian of a map is. And that's all I've done here. And these were all t's. I better put the t's in on the ht. So what have we learned? So the time derivative of the Jacobian, how much, if I look at a little bit of area, how much that area changes from hyperbolic surface to hyperbolic surface? Well, it's h dot minus 2t v naught squared over h0. Got to take the derivative on the t. It doesn't matter because I'm at t equals 0. And the only way, and so what I find is that Jacobian vanishes identically to first order. To first order along this family of harmonic maps, you don't see a change in hyperbolic area density. This is, as I'm pausing, historically this was really cool. This is a very fast proof of what's called Alfor's lemma, which is in 1961. And it was sort of crucial in a number of applications. So this is all at t equals 0. Oh, you want me to say at t equals 0? Okay. Oh, okay, okay. All right, well, that was fun. Let's do 18 or 23 minutes. Let's do second derivatives. Okay. Let me see what I can get away with here. So let's do second derivatives. So the energy, I'm going to take something off the energy in a minute. The energy, we have said, is h plus t squared v squared over h. Okay? And I have said that the Jacobian is h minus t squared v squared over h. This is the total energy. If I take off the Jacobian, well, I'm going to integrate the Jacobian. Ooh, yeah, does that make sense? Right? Here's the integral of the energy density is the energy. The integral of the Jacobian is the integral of the Jacobian. Okay? There's no magic yet. Now there's magic. The integral of the Jacobian is the area of the target. Right? These are hyperbolic surfaces. They all have the same area. The area of m rho, whatever m rho is by Gauss-Bonnet minus 2 pi times the Euler characteristic. It's always the same. So this is some constant. So the energy minus a constant is this, but now, the h's cancel. So what do I get? I get 2 t squared v squared over h. There's t's in all of these. Right? So if I want to take second derivatives, so the second derivative of the energy minus the second derivative of a constant, which is 0, is the same as the second derivative, again, at t equals 0, of this quantity. But this quantity has 2 t's in there. So if I'm going to take 2 derivatives and get something non-zero, I better only take derivatives of the t. Right? So what do you get? So this is 2 times the integral t squared v squared over ht. Doesn't really matter what the derivatives of h are. And I get the integral of phi squared, I guess there's a 4, divided by h0, which was 1, and that's it. Okay? So now I roll the dice. So Keith talked about this quantity. Yes, he did, because he told you about something called the Weil-Petersen metric on Teichmuller space. And so we have some second derivative of energy is equal to this Weil-Petersen metric. How does that make sense? Well, the point is that energy minus 2 pi chi has a minimum at rho equals sigma. Why? The identity map, so I'm going very fast, but so I apologize, but you won't understand the next few, you may not understand the next sentence, the sentence after that, there's hope. Okay, when rho is sigma, the harmonic map is the identity, the energy is the energy of the identity. The energy of the identity is the area, 2 pi chi. Everywhere else, it's more than area. Sum of stretch squared is more than stretch times stretch, which is area. Sum of stretch squared divided by 2 is more than stretch times stretch. So this has a minimum here. So I have this function. And here I'm thinking of a map from the Teichmuller space to R, and it has a minimum. A function with a minimum, so it's critical. At a critical point, the Hessian of a function is a tensor. In other words, it only depends on, if you evaluate it, it only depends on the tangent vectors to paths, not their 2 jets. So it's a tensor, so it's a metric. So in hindsight, knowing that we're at a minimum, we should have been asking, what is the metric associated to that function, to the Hessian? Hessians provide metrics. So here, we get really excited in hindsight because we had a function with a minimum, so we had a new metric on Teichmuller space, the Hessian of it. And what is that new metric? It's the oldest, one of the older metrics. It's the Weil-Petersen metric, okay, which Keith gave some lectures about the curvature and other aspects. Okay, now, one comment. Oh, can I do this? I really want to do this. I can't do it. Okay. Oh, I can't do it. So I'll say something like, we can do further computations and prove, and this is really in a paper of Yost, that from this point of view, if you keep taking derivatives like we're taking here, you can prove that the Weil-Petersen metric is Kähler, you can find its curvature tensor. And what I really wanted to do for you was I wanted to work out something else. Okay. It won't work, I won't start. Okay, so there's a lot of Let me summarize it this way. If I look at W star rho t, and that's t phi 0 plus this stuff, dz dz bar plus t phi 0 bar, then through this calculus we've talked about, we can write this as t phi 0 plus big O of t squared plus t phi 0 bar. So I know the expansion easily to first order, but in fact, we can keep going to all orders by playing the same sort of game we've played. And once I know the metric, once I know a sort of expansion of the metric, I can compute many things. And I'm sorry to leave it there, but I think I should. In order to talk about the global theory. Let's leave that there. Okay. More maximum principle. Maybe you've noticed the theme. There's sort of a point, so you're supposed to notice the theme. Let me try this. Have you folks met a Beltrami differential for a map? Yes? Let's vote. I know what a Beltrami differential is. One vote yes. I don't know what a Beltrami differential is. 11 votes no, some almost at chin level. Okay, so if I have a map W from a surface with a coordinate to the surface with a different coordinate, maybe it's a conformal map. In other words, maybe it preserves angles. Maybe it doesn't. How would you tell? Well, what you would look at is an object nu, which would be wz bar over wz classically, dz bar over dz. Okay? The point is that because if I'm thinking about dw as a form, I would write dw as wz dz plus wz bar dz bar, and that's not dz because it's got a dz bar part. I don't really care. So let me isolate the dz bar part. Let me just pull out a wz. I don't really care what goes in front of this if I'm only interested in conformality. And so what I have is wz bar over wz, dz bar, and this is measuring the difference from being a multiple of dz, so I care about that, and I call that the Beltrami differential. It's a characteristic tensor associated to a map between surfaces. Great, so it's, I said let's look at phi and h. I could have looked at phi and the Beltrami differential. If I wanted to look at the phi and the Beltrami differential, then the Bachner equation becomes, and let me look at the function log of 1 over nu squared. Okay? Notice that when this Beltrami differential is 0, wz bar is 0, the map's conformal. When the most extreme case is when wz bar over wz, when it's nearly 1. Okay? We know that the Jacobian, as we've said, the Jacobian of a map is wz squared minus wz bar squared. Typically we're interested in orientation preserving maps, so it's very extreme when the map is squeezing a lot. And when it's squeezing a lot, the Jacobian is small, which means that wz and wz bar are close to each other. Okay? So the ratio is always a little less than 1. It's extreme when it gets close to 1. Okay? So I can look at the Bachner equation for this. Trust me, the Bachner equation looks something like, when I rewrite this, up to a constant, 2t phi sinh g. Okay? I like this equation. I like this equation a lot. I have something convex and increasing. I pulled out a t in front as a coefficient. And since g is at least g, and that makes it easy to start comparing solutions. Okay? So, the maximum principle, again, I can look at the equation for d by dt g, not at 0, everywhere. Take this equation, differentiate it in t. G depends on t at every time. Okay, you get an equation for g dot. You apply the maximum principle, and you find something amazing, that g dot is always positive. In other words, along this family of harmonic maps corresponding to a ray, the Beltrami differential at each point gets larger and larger. The map only ever squeezes more. It stretches, it just keeps stretching in the directions of the maximal stretch direction, and it actually shrinks in the other directions. The ratio gets smaller and smaller. Where does it go? Okay, so there's a monotonicity about the rho t on these rays. So what does that tell me? This is all about technique. This is probably a very poor use of my time if I want to say phenomena, but don't want to do it that way. It's the wrong picture. But nevertheless, somehow I think technique is important at this moment. Remember, I have some zeros for phi 0, and I have some places where I'm not 0. And what's happening is, if I'm looking at t phi 0, the divisor is fixed, and the coefficient is growing. T phi of z dz squared. All this is fixed, and it's always just getting larger and larger. So the zeros are the same, and things are spreading. And so, if I look at let's center. Put my divisor here for a minute. Move this one over there. This Beltrami differential on this little ring is getting bigger and bigger. Right? After a while, it's like a quarter. It's some non-zero number. So in log of 1 over it, well, that's going to be like log 4, some number. And if I take an annulus, over here, it's going to be like log 7. Okay? Now, what happens in between? I know it's like log 4 here, and it's log 7 there. So those are boundary values for this differential equation on an annulus. And what happens on the inside? On the inside, I have the coefficients are getting very, very large on the right-hand side. I don't know much about GT, but this is getting very large. So if you think about what is going on in terms of an ODE, if this is R naught and this is capital R naught, and what I'm saying is that here's R naught, and I graph this G, well, remember I'm at like log 4 here, I'm at log 7 there, and I'm looking at a differential equation that's roughly G double prime equals T times since G. What does your ODE theory tell you? This is positive, so it's a convex graph, but it's a convex graph with a huge second derivative. So that means that this thing is being driven down to 0 very rapidly. So what have we learned? We learned that in the middle here, this Beltrami differential, this Beltrami differential is very, very small. Sorry, it's very close. The Beltrami log of 1 over, it's very small. The Beltrami differential is very close to 1. The entire map is stretching. Is collapsing in the vertical direction and stretching in the horizontal direction. So our picture of the harmonic map looks like this. So here's, I'm drawing the horizontal foliation more or less vertically because I need things to fit on the blackboard. Maybe up here it branches again. Okay, so I have some picture like this, say on the universal cover. That's the quadratic differential. What does the map look like? Well, this stretching that we're talking about and the shrinking means that these lines are getting stretched very, very long. They're being stretched, actually, if you compute it, like root t. And these directions for the vertical, in the vertical direction, they're getting shrunk. So this is on the quadratic differential picture on sigma. Back on rho, what is happening is these are getting pinched, and in fact, if you do a few more computations, you can work out that the geodesic curvatures are getting small. The point is that these become very close to some ideal triangle, or ideal, these become very close to a geodesic, down, so do these. Let's see if I can draw this. Something like that. Up here I have another one. Oops, they're not supposed to cross. And so that's the picture on the target. These leaves are getting very close together, they're becoming geodesic. And I had some picture, which is not very good, where it looks something like this. I have like an ideal triangle forming here, ideal triangle forming here, ideal triangle forming there. And these lengths from here to here, if this is A, then the length here is t to the half times A. Okay? Well, I don't like that t to the half. That's really large. Well, it's not going to hurt things if I divide. How am I going to do this? I guess I should have gone for. Let's just divide by t to the half. That'll keep all the lengths measurements bounded. But if I divide by t to the half, I'm dividing a hyperbolic metric by t to the half. So the curvature is going down by t. Okay? And so for very negative curvature, so now I have now I have a constant curvature metric of curvature minus t. And so what that means, let me maybe not fill in these lines. I'm going to get a picture that looks, that first ideal triangle will look like that. The next ideal triangle, now is also, now this I can't draw. What am I going to do? This was a lot easier last night. Oh, I see. That next ideal triangle gets crunched as well. Now my distances are back to being around A. And the final ideal triangle is like this. Do you see the kind of body of it in here? So here are my ideal triangles getting crunched. In the limit, as t goes to infinity, what we get is something tree-like. Like that. Does that make sense? That's a sort of, so when we rescale on the harmonic maps, we get something tree-like. On the other hand, this leaf space, if I look at the, if I just collapse in the blue directions, in the vertical directions, if I look at that harmonic map that just went z goes to x, I get something tree-like. No, it's... In fact, I get the same tree. Right? This construction of straightening and collapsing is the same in the limit as this construction of just collapsing. Okay. So how to understand this? So here's what's going on. We have Teichmuller space. Here's sigma. Here's my vector space. Here's my ray T phi 0. That gave rise to a family rho T. We've just seen that if I look at those, what rho T looks like, it's just describing the metric, rho T starts to look like a tree with some metric space. This is very much a cartoon. This really is what's called an R tree. And so the boundary points of Teichmuller space can be imagined as R trees as pi 1 of m group actions on R trees at infinity. Okay? That's what has emerged here. And the interesting part is that these harmonic maps converge. So what we've seen is that the harmonic maps from W, from m sigma to m rho T, as long as I rescale, converge to a harmonic map from m sigma to a real tree from phi constructed from that Hopf differential. So this boundary is what is known as Thurston's boundary for the Teichmuller space. It's quite famous, more than 40 years old. Thurston used it to analyze diffeomorphisms of a surface. There's a very elaborate theory there, and beautiful theory. And we see it starting to emerge from these harmonic maps and these holomorphic objects associated to harmonic maps reflecting representations into SL2R. And there's a lot of current research going on into somehow understanding what limits of harmonic maps corresponding to representations and say into SLNR might look like, and how much of this model extends. Instead of looking at R trees, we would imagine R buildings, and the situation at the moment is actually quite murky. So we're in the stage where there are some serious, substantial results. There's nothing like the cleanliness of this picture is nowhere replicated. I'm sorry I ran out of time. I'm sorry I ran over. Thanks for sticking with me.
Any questions?
Yeah. Oh, that's a good point. So the question was, thank you, I'll have to owe you a drink. How does this depend on the base point sigma? The whole point is actually that the base point sigma washes out of the discussion. Because this object T, this object tree, is only related to the vertical foliation of this quadratic differential. So if I had a different sigma, I would end up with a path with the same vertical foliation, and the same tree would necessarily emerge. So in fact, in the limit, this fixed base point, this ad hoc choice of base point sigma, is no longer relevant. And that one can argue for that in some sense by thinking of, where's my picture? Here with this t to the half if you can work out lengths of curves, and the curves will basically cut across ideal triangles and just really get stretched only by the t½ here. That's very, very vague, but that's the reason.
Any more questions? Okay, so if not, let's thanks the speaker.